Today, we are pulling back the curtain on something you probably never think about, but it keeps our entire world standing. It's the invisible digital safety net that makes absolutely sure our buildings don't fall down and our bridges don't collapse. This is the secret that keeps us safe, and it all happens long before a single bolt is ever tightened.
I mean, really think about that for a second. How do they know? With a skyscraper or a massive bridge, you can't just build it and hope for the best, right? There is absolutely zero room for error. So how can they be so certain that it's going to be safe?
Well, the answer is pretty incredible. They use powerful simulations. They build and they break these enormous structures hundreds, sometimes thousands of times, all inside a virtual world. They can find every single potential flaw, every little weak point before a single piece of concrete is ever poured. And it all happens inside a computer.
But, before we dive into the software that makes this all possible, let's just quickly get a handle on what these structures are up against in the first place.
Because here's the thing we forget. A building isn't just sitting there. It's in a constant, invisible battle. Gravity is always trying to pull it down. Wind is trying to push it over. And in some parts of the world, the very ground it's built on can start to shake violently. So a building isn't just a static object. It's an active system that has to resist immense forces every single second of every day.
So how in the world do you fight back against these invisible, powerful forces? Well, you create an even more powerful digital safety net. And this is one of the main tools in an engineer's arsenal. It's called STAAD.Pro. Now, don't think of this like a simple drawing program. It's more like a digital twin of the real world, a virtual playground where engineers can build a full-scale model of their structure and then just throw everything at it. Hurricanes, earthquakes, massive loads, you name it, they can simulate it.
And what's really amazing is just how deep this goes. Engineers can tell the software, okay, this beam is concrete, this one's steel, this one's timber. Then they can apply any force imaginable from the building's own weight all the way up to a full-blown earthquake. And here's the kicker. It does all this while constantly checking its work against super strict engineering safety codes, and then it spits out these incredibly detailed 3D models showing exactly what happened.
So how does this actually work in practice? Let's walk through how an idea goes from just a simple drawing to a living, breathing virtual structure.
It pretty much always starts right here, a flat 2D architectural plan. This is the vision, right? The blueprint of what needs to be built. But at this stage, it has no substance, no strength. It's literally just lines on a page.
Then the software works its magic. It takes that flat plan and transforms it into a 3D wireframe. It's basically the digital skeleton of the building. You can see its shape, you can see its form, but it's still just a ghost. It doesn't weigh anything, it doesn't have any real physical properties, yet.
Okay, this is where it gets really cool. The engineer starts bringing this digital skeleton to life. They assign real-world properties to every single component. This beam? Okay, that's now concrete, and it's 0.23 by 0.45 meters. These columns? Same thing. And that truss over there? That's now high-strength steel. The digital ghost is finally becoming a real, physical object.
All right, the virtual building is now complete. It's been built piece by piece inside the computer. So what's next? It's time to try and break it.
This stress test is a really methodical process. First, you have to tell the software how the building is anchored to the ground, just like in real life. Then you start applying all those forces we talked about. But the really crucial step is combining them to simulate the absolute worst-case scenario. Think about it. What happens during a powerful earthquake and high winds? They test for that. Finally, you hit run, and the software calculates what all those combined forces do to every single part of the structure.
And these loads are super specific. You've got the dead load. That's the building's own permanent weight, the concrete, the steel, all the stuff that's not going anywhere. Then you have live loads. That's all the temporary stuff. People, furniture, cars driving across a bridge. And then, of course, you have the big ones, the incredible force of wind, which is a huge deal for skyscrapers, and the violent shaking from a seismic load. Literally every possibility is accounted for.
So the computer has run all the numbers. The virtual storm has hit the virtual building. What does the result even look like? And what's the one thing, the only thing, every engineer is hoping to see?
And this is the result. It's amazing. On the left, there's our simple digital skeleton. But on the right, after the analysis, we get this incredibly detailed color-coded map that reveals all the invisible stress points. It's called a bending moment diagram, and it shows an engineer exactly where the structure is under the most strain, where it's being bent, pulled, and compressed.
This software gives them unbelievably precise data on everything. Bending moments show where things are being stretched or squeezed. Shear forces show where a beam might literally get sliced apart by opposing forces. And deflection, well, that shows how much a floor or a beam will physically sag under all that pressure. This is the language of structural safety.
And this, right here, this is it. This is the whole point of the entire exercise. It's getting a clean report. 0 errors, 0 warnings, and 0 notes. That is the digital proof that the design can handle everything thrown at it. This is the engineer's green light. It means the design works.
So, the most important number in all of this isn't some huge, complicated figure. It's 0. It doesn't mean nothing happened. It means success. It signifies that every calculation, every material choice, and every connection has been validated. It means the structure is safe.
So what does this all really mean for us? The people living and working inside these structures every single day.
Well, it means this isn't just some fascinating theoretical exercise. This incredibly rigorous process of digital modeling, stress testing, and redesigning over and over again until they get that perfect 0 error report, this is exactly what keeps our world standing. It's done for every major bridge, every stadium, and every skyscraper.
So if we boil it all down, what's the big takeaway? It's that modern complex structures absolutely require this kind of complex digital testing. Software like this lets engineers see into the future, find a potentially fatal flaw, and fix it with a click of a mouse instead of a wrecking ball. And that ultimate benchmark for success, that holy grail, is always the same: a perfect, clean, 0 error report.
It's a pretty powerful thought, isn't it? Our physical safety in the real world so often depends on this intense, invisible battle that takes place in a virtual world, all striving for that one perfect number, 0. Something to think about the next time you're on the top floor of a skyscraper.